All right, let's see. Good morning, everyone. That's sufficiently light. I'm sure I will be thoroughly awake by the end of this session. Okay, so I'm going to talk about a HSM prototype that we have built. But first, short introduction. My name is Fredrik Stromberg. I'm involved in these companies. I'm not going to go into detail, but in short order, they are Mullvad VPN, which does a VPN service, and we also have a browser based on Tor browser. There's Tillitis, which does open source hardware. There's Glasklar Teknik that does Sigsum, the transparency log, system transparency, which is a combination of remote attestation, reproducible builds, and transparency logging. On paper, right now it's a glorified bootloader, but we keep getting distracted building transparency logs and hardware. And now we also run the Debian snapshot service, which is a few hundred terabyte disk array with a bunch of Debian packages. And there's Karlstad Internet Privacy Lab AB, which does traffic analysis defense against AI-based classifiers. So we started 15 years ago, and eventually we became obsessed with, I'm talking about Mullvad here, obsessed with what trust assumptions do our users have to, what do they have to be vulnerable to? And we ended up with system transparency and trying to reduce the trust assumptions and make them more explicit. And then we realized that for system transparency, we needed a transparency log. And we started building one. And sometime later, Tillitis was founded, and we announced the TKey. And earlier this fall, we announced the existence of an HSM prototype, which I've dreamt about building for many years, but it's felt a bit too ambitious until now. Right here, unfortunately, this is the wrong, this is an earlier version. We now have an actual PCB, which is not made out of super glue and silver tape. On the left-hand side, you have the Tillitis TKey, which you can think of as a trusted execution environment on a USB stick. You can also think of it as a computer that does measured boot and uses that as a key derivation function. It is also the most open source hardware, firmware and hardware USB security key that I know of. The PCB design, the schematics are made in KiCad. They are on GitHub. Same thing with the HDL, because there's an FPGA on there. Same thing with the firmware. And we reverse engineered the programming and locking protocol for the on-die NVCM OTP memory, so you can program it and lock it with open tooling as well. And of course, we use the USUS toolchain with NextPNR, so you can synthesize your Verilog all the way and put it on the ICE40. And on the right-hand side is our HSM prototype. What is an HSM? Well, basically, it's like a YubiKey, except or a TKey, except it's more powerful. And there's usually also a notion of physical security and tamper resistance, or tamper detection, or tamper reaction. So you have this computer. It holds keys that are very important to you, perhaps some type of signing key. You do operations using those keys, and you have tamper sensors like pressure or temperature or vibration or GPS position or other things. The HSM market today is mostly an oligopoly consisting of unverifiable proprietary black boxes. And wouldn't it be nice if instead it was slightly more open? So that's what we're trying to do. These are my favorite. This is my sort of design philosophy. I've been interested in cybersecurity since I was 12, and I come from a family of inventors, so I like thinking about creativity and strategy and in my case, cybersecurity at the same time. And I like to decompose things until you find the atoms, right? So if you, in physics, if you can find the underlying fundamentals, it makes it a lot easier to reason about nature. And I think the same goes for cybersecurity. The question is, which design primitives are the most long-lived, the most fundamental, give you the most bang for the buck? Because, as we all know, more and more complex systems are inevitable. If you want more features, you need more logic gates or more machine instructions, and so you have this graph where, with increasing complexity, you have the expected and intended behavior of the system, and you have the actual and surprising behavior of the system, and the delta between these two lines is your attack surface. And so that begs the question, with more and more complex systems, with more logic gates, higher clock frequency, more lines of code, how do we keep these two lines together so that the intended and expected behavior and the actual behavior of the system are the same, more or less? And I like hardware defenses, because hardware defenses, they set the rules for software. Software can't do things that the hardware doesn't allow it to do. Cryptographic defenses are nice because they allow us to create security margins that we can express in terms of how many exajoules of energy, how many Dyson spheres of ideal computronium, and how many millennia do we need to crack this one instance of AES. And if you knit things together, symmetric ciphers, forward secrecy, integrity protection, authentication, then you get a new concept. Secure communication channels. It's the same thing with transparency logs, right? We just knit together Merkle trees, hashes, and public key crypto, and then we get transparency logs. So those two are very nice. Obviously, restricting the state space is also a nice thing to do. I think we should think about software as the purpose of software is to converge the reachable state space of the running system on the set of behaviors that you care about and not the set of behaviors that the attacker cares about. If we had infinite money, we could just produce hardware that did exactly the thing we wanted, but alas, we have to amortize the cost by buying things that are chips that are programmable. But yeah, software is used to make it less programmable, or we have a boot chain and we want it to be a web server or a WireGuard server and not part of a botnet, for instance. Distributing trust assumptions is also nice. You can do this with multi-signature schemes. You can do this with multiple branch instructions in a row that give you some amount of glitching protection, or perhaps you have cores running in lockstep. And of course, you want the specifications and the implementation and the supply chain to be as available and understandable to you as possible. The HSM that we are building builds on the TKey, which I described before, the USB Armory, which is a fantastic device, which I'm very grateful that Andrea and his colleagues started working on many years ago. It runs Tamago, which is a fork of Go, that you run bare metal on the device, and now you can also run it on x86. You can even run it as a bootloader or in UEFI. The UEFI context. And then we have the Cryptic HSM, which is a project created by, among others, Joachim Strömbergsson, which is, and Linus Norberg, who is also here, and some other people. It's a collection of primitives, open source hardware that you can use to build, for instance, an HSM. I believe OpenTitan uses some of Cryptic's cores. We certainly depend on a lot of their work, and they also have designs, things related to like how do you build a good TRNG and things like that. So we tried to take the best ideas from these three projects and then bunch them together in something new. And it looks like this. The three critical chips are the NXP IMX6, which is an ARM core running Tamago, that's bare metal Go. We have the ICE40, which is the same FPGA that we use for the TKey. It runs 32-bit RISC-V core and some other things. Then we have the ECP5, which is a larger FPGA, also from Lattice. It has around 80,000 logic cells, so much bigger than the ICE40's 5,000 logic cells. And that one also runs a TKey design, but with additional cryptographic accelerators in the memory map. And then there's some RAM and some micro SD slots, and the current prototype doesn't have any tamper sensors, but as you can see, that's the idea. Okay, and then there's Sigsum. Most of you, I'm not gonna. So, as probably all of you know already, but I'll just give a short summary. So, in a transparency log context, we have a few actors. In a transparency log with distributed trust assumptions, we have additional actors or components. There's the log, of course. There's the, or without the transparency log, you have the signer and the user, right? And so you get signatures that give you authenticity. If you have a transparency log as part of your client's trust policy, you get signatures that give you both authenticity and discoverability. That's how I think about it. And of course, that requires requires the signer to send, in the case of Sigsum, a signed checksum to the log. And we have witnesses that witness the log and make sure it's consistent from their network vantage points. The log provides a proof, a co-signed proof, to the signer, and the signer sends this proof to the user as part of the usual software release process or whatever. And then, crucially, as Filippo likes to remind us, there is the monitor, hopefully, that monitors the log and discovers key compromise or key misuse. Let's see. I'm doing it really well on time. Is that right? Do I have 7.5 minutes left? Yeah? Okay. Wow. Whoa. I mean, did I just ramble through that thing? Was it coherent to you? Okay, fantastic. I'm sure I woke up, maybe a bit later than the rest of you. I don't know. In any case, okay. So we're gonna do a demo. The demo is not going to include everything that we actually have. So if you want to see the HSM prototype up close, we have a few with us. I also have a bunch of my colleagues here that are more than happy to tell you all about the technical details. And of course, there's the hackathon room on the other side, where some of us will sit with our laptops and do things with this prototype, and we can show you. Basically, actually, I think I'm gonna tell you about our future plans, and then I'm gonna go back and describe the HSM a bit more, and then my colleague will come up here and do a demo. Okay, so basically, our future plans are to productize this prototype. Again, it's currently a prototype. We don't know when it will be done, and it does have some limitations, but hopefully it will be the most open source hardware HSM there is, which is fun in itself. And the engineering challenge is to make it fairly secure against physical attackers don't seem insurmountable, at least if you in terms of getting it NIST FIPS 140-2 certified, or at least have the equivalent type of security. So that's interesting. Separately from this, we also have plans to do open source silicon, which has nothing to do with transparency logs, but it does have something to do with transparency. The short version is that thanks to Google and Tim Ansell and Skywater and eFabless, there was a way to do tapeouts, open source silicon tapeouts using tiny tapeout, and you go through eFabless as an MPW service, and Skywater would provide you a tapeout. eFabless unfortunately shut down the company earlier this year, but now there's a new MPW service by Tim Ansell. So if you go to wafer.space, you can buy things from the GlobalFoundries 180 MCU process. And the reason you will be able to do that is because we are funding Tiny Tapeout to port their tooling flow from Skywater to GF180 MCU. And what's also exciting is that this will probably that PDK and that tooling will probably, and that process will probably allow us to go all the way down to, I think, 55 nanometers, because it's the same equipment. So if you like open source silicon, check out Tiny Tapeout and wafer.space, and I'm more than happy to preach about those things as well. Okay, so what is running on this thing? We have the host computer, talking to the IMX6, running Tamago. The IMX6 in turn, I'm going to describe things as we envision them, and we have plans to change this, but the idea is that not only do you measure the software, not only does the firmware measure the software that you put onto the HSM, a thing that differs between the HSM and the TKey is that with the HSM, we also intend you to be able to measure the bit stream. So the ICE40, the IMX6 sends a bit stream to the ICE40. The ICE40 configures the ECP5, and thus you can have not only measured boot, but also measured hardware, which is fun. And the idea is then that you have the cryptographic key material in the ECP5. I'm sure all of you have a lot of questions about the security of those buses and so on. And yes, there are limitations, and yes, there are some better and worse solutions to those limitations. But that's the gist of it. So measured hardware is fun. Okay, now I only have 2 minutes left. Shall we do a demo? It's a very short demo, but nevertheless, it's fun. Okay.
Hi, everybody. Can you hear me? My name is Daniel. I'm Fredrik's colleague then, obviously. So, yeah, we're going to do just a brief demo to show that something actually works here, okay? So, and just so you know, we sort of hacked this demo together yesterday during the breakout session, so fingers crossed. But first, a more recent picture of the hardware then. We also have it here, and you can look at it on the breakout session later. But it's a credit card-sized PCB, with a bunch of ICs on it, as Fredrik mentioned. We got the IMX6 sort of facing the terrifying world, providing us with different interfaces that we can use. And as Fredrik mentioned as well, usually in the TKey sense, we have 2 applications running, one on the host, which could be a server or a computer or whatever, and something running on the TKey. For this instance, then, the HSM can do all of that. So it's running both those applications, more or less. So in here, we have a Tamago instance running on the THSM right here. And it provides us with a network interface, and we can simply do SSH to get into it, and we get a lot of different commands we can do. Are you able to read this? Yeah, sort of. So we can talk to the FPGAs beneath the IMX6 then. We can just ask it for the UDI or the name of the FPGAs running there, and it says something about TK1 and the MKDF version 5. Sounds great. But we can also then interface with sort of the secret stuff down there, like the the encryption keys and stuff like that. So we can type TKey and sign, and we can sign something like TDS 2025 or whatever, and it will now interface with the FPGA, load an app right now. That might not be how it's done later, but yeah, we get something back at least. And I guess that's the gist of it.
Yeah.
We have more applications. Oh, thank you. We figured, what is the conference without hardware on stage, right? Yeah. But we have, as Fredrik mentioned as well, we have another demo as well that's tying more to transparency logging, but let's do that one in the breakout session later if anyone is interested.
Yeah, I could actually.
Great.
Yeah, thank you. Awesome. So I'll. Before we end, I'm just gonna give a short description of that. So you can think of it. So in terms of transparency systems, what can you use an HSM for? And I roughly see 3 possible use cases or three applications. One is that you protect the 4. You can protect the signer's key, obviously. You can protect the logs key, or you can protect the witness's key. And you can also create an app that only signs things if they are already transparency logged, which I think is quite an interesting way of adopting transparency systems, because as I'm sure you've all thought about, if you want discoverability, the client has to fail closed, right? It can't opportunistically say, oh, there's no inclusion proof today. Well, I guess it's fine anyway. So the client has to fail closed, which means you need long-term reliably available logs and witnesses for your trust policy. And then you have use cases where you're not going to be able to have a trust policy that includes these things, because maybe you're using, I don't know, Intel Boot Guard or use UEFI Secure Boot, which only supports RSA. So what you can do in that case is you protect your RSA key on the HSM side, and where the HSM doesn't sign any hash, you send it, it only signs hashes that are already in a log. So that's a nice way of gradually having organizations gradually adopt transparency logs without having to mess with the trust policy on the client side. So those are just 3 things that we're building. We have a bare metal C implementation of what I just described. I believe it's 80 kilobytes, including all the ECC stuff, so it's still a bit big. But yeah, so we can talk more about that offline later. All right, thank you all for listening.
Thank you, Fredrik. Does anyone have any questions?
Yeah, great demo. And in the direction of productizing this HSM, what are the major functionality to be in par with like Utimaco and Thales? And the second question, what is the current status or plans for supporting post-quantum algorithms?
Good questions. So on the first one, we have a lot of work left. I mean, the thing is not going up in smoke. It runs things. We have done, we're running time ago. We're running things on both FPGAs. But before we start selling it and telling people that you can use it for production use cases, there's a lot of things left to do. The PCB is also just a prototype. I expect that will, one thing we haven't delved deeply into yet is what tamper sensors do we want? What type of epoxy are we going to use? Are we going to have a metal mesh? Are we going to encase the thing in something? Perhaps tungsten carbide? There are a lot of questions that need to be answered. And regarding post-quantum primitives, we certainly want to do that, and we're well aware of the need, but we haven't gotten there yet. Yeah. More questions?
Cheers. Yeah, thanks. Thanks for a great talk. I was just curious, and maybe you actually mentioned this, but will the HSM firmware be open sourced as well?
Yes, of course. So
great.
Just like the TKey, the HSM's schematic and PCB design are made in KiCad, and we'll be open sourcing that. Same thing with all of the HDL running on the FPGAs, and same thing with all of the firmware and all of the applications. So the entire thing, except for the ASIC designs, which we don't have access to, obviously, will be open source. And in all cases where it's possible, it will be BSD licensed.
Yeah. Nice. Thanks.
My goal was to keep you busy, so I actually have a couple questions. The first question is, have you thought about how you might use T-logs to be able to measure or capture state of the hardware at the same time, not just the hash, only incorporate when, but that same transaction could cover both in theory, which would make that more guarantees about that operation external to the HSM. That was something that you can't get out of an HSM today. The second thought, kind of in the same spirit, is what is the performance overhead of that logging exercise? The sort of the third corollary is like what the TPS expectations you have for the algorithms that you're supporting.
All right. So thank you, Ryan. Regarding the first question, I'm not sure I understood exactly what you were asking. So we can let's take that. Yeah.
Secure boot and
okay.
The PCR equivalent, sort of.
Okay. Yeah. So the we're gonna try to make so the ICE40 and the ECP5 running 32-bit RISC-V soft cores. They are doing unconditional measured boot using the DICE approach and. I believe we can make the IMX6 do the same thing, but we haven't done that yet. When you have once you have that, all you need is persistent storage, and then you can make that into verified boot. And then you also have the flexibility of describing whatever trust policy you want. So we definitely want to boot as much of it as possible with M of N signatures, and then signatures for reproducibility, and then discoverable signatures, and so on. So absolutely. The third question, TPS. No idea. We don't know yet. And the second, overhead. We don't have right now, but we will have eDDSA accelerators on ECP5. So that should be nice. The overhead for T-log verification on the TKey, however, is quite substantial. It takes about 15 seconds. Then again, it's a very open and tiny device, and you can audit the entire thing in not that much time because it's only 5,000 LCs. So, okay.
Are you considering having polynomial operation accelerators also, so we can have post-quantum cryptography on those devices?
We will definitely have post-quantum support eventually, and I expect that some of that will be accelerated in hardware.
Right, I think I'm going to stop it there so we can move on to the next talk. A
All right.
big hand for Fredrik again.
Great, thank you.